My dear people, look at this particular pipe. It is tilted at an angle, and that the section 1 is at a height z1. Let us say it is at a height of 5 meter from the datum. Datum is always taken to be 0. Datum is nothing but the baseline. Yeah. And z2 is, let us say, 7 meters. Otherwise section 2 is at a height of 7 meters from the datum. So this means when water is flowing inside this pipe, in order for the water to move from section 1 and to reach section 2, it has to do some work against gravity. Ah, so it has to exert some energy. So, what is going to happen to the velocity with which the water is going to flow out? Is that going to affect the pressure with which the water is going to flow out? Oh, what's going to happen? Aha, that is what we are going to be seeing. This dude down here, he said something very interesting. But before that, I have a question to all of you. Okay, so here we have a pipe, and let us say that there is a water of this cross section. Yeah, water of this cross section is flowing from section A, which is at a height of z1, let us say 5 meter, and it is flowing all the way. It is acting against gravity and it's going up and reaching z2. Let us say z2 is 10 meter. Yeah, so my question to you all is this. So let us imagine if a fluid particle has a energy, a total energy of 10 joules over here. When it reaches this point, let us call this point as S. When it reaches this point, what do you think is going to be the total energy? Because it has spent some energy going up, is it not? So what do you think? Do you think the energy will be higher or lower than 10 joules, or do you think it's going to be the same as 10 joules even though it has moved this distance? What do you think? Huh? What? Okay, okay. So you say that it's going to be less. So the total energy is going to be less than 10 joules. So let us say 8 joules. Okay, okay. I understand. Logically, I understand what you're trying to say. So let us say this particular section of fluid moved from here to here, and then it still goes further up and it reaches this particular section here where the diameter is also larger. Now, what do you think is going to be the total energy at section 2? What do you think? What is it? It's going to be lower, is it? Okay, 6 joules of energy. So, what has happened to that 4 joules of energy? Huh? What is it? I see. I can understand what you're trying to say. You're trying to say that the fluid has exerted that energy, it has spent that energy, that 4 joules, to start from here and then reach over here. I see what you mean. Okay. Well, it is logical, to think like that, is it not? Because the diameter is different, so the area is different here, and also it has got to go against the gravity, etc. Ah. But then, as I told you, this dude over here and in this corner, yeah, he is a very clever person. Yeah, he said something very interesting. Shall I tell you what he said? Yeah, he said that in a steady flow the fluid does not gain or it does not lose energy. Yeah? Otherwise the total energy of the fluid is always conserved. What does it really mean? Okay, it means that if the fluid over here, if it starts with a total energy of 10 joules, when it reaches here the total energy is still 10 joules. Can you believe it? And when the fluid goes all the way up here, even here the total energy is still 10 joules. What is happening? How is this even possible? Huh? So, according to what he says, no matter which point in the flow you take, the total energy it has is always the same. What? Okay, now, my dear people, we are always talking of the total energy. So, what are the different types of energies that this liquid that's flowing has? Tell me. So, okay, let me tell you. It has the pressure energy, yeah, plus it has the kinetic energy. Otherwise, since the liquid is moving, it has some kinetic energy. Plus, since they are all at an elevation, yeah, they also have some potential energy. Plus they also have some thermal energy, but we assume that there is no heat going inside or outside of the system, so we just assume it to be we just assume that there is no heat. So the total energy in a fluid is the pressure energy plus the kinetic energy plus the potential energy. So according to what Bernoulli says, if you add all these three energies in this section, it is exactly equal to the energies over here. So how is this possible? Let me tell you very easily. The potential energy will become kinetic energy and vice versa. Yeah, so that is how the total energy is always conserved, no matter where you take total energy, here, in this section, in this section, in this section, it's always the same. So can I write it as total energy at 1 equals total energy at 2? Some of you might be thinking, well, so what? Oh my goodness, this has got so many important applications and implications in fluid mechanics and also in our daily life. Well, I'll explain you how. Okay, before we go into this, you might be asking, well, Venkat, the previous pipe that you showed us was a very simple pipe. What about this pipe? In this pipe, is the total energy, if the total energy here is 10 joules, is it still 10 joules here? Yes, it is. Is it still 10 joules here? Yes, it is. The total energy is always conserved in all these sections. And then, even if a pipe is like completely different shape, the total energy over here in section 1 equals the total energy in section 2 is equal to the total energy in section 3. This is so cool, is it not? Now look at this particular example in which water is there, let us say at an elevation of 2 kilometer. Yeah, and this elevation is, let us say, zero point 0.5 kilometer, otherwise 500 meters. Yeah, water is flowing, water is rushing through a pipe, yeah, from one tank to another tank. So the total energy of the fluid in this section is equal to the total energy of the fluid in this section is equal to the total energy of the fluid in this section. This is unbelievable.